Welcome to NSF Live, to another episode of Europe's Future in Space. This time for real and not like last Friday, I guess. And, there's been a lot of companies around. There's already been 8 episodes. This is going to be the 9th one. So, without further ado, let's talk about some of these Aerospikes that we're already showing here behind me.
And here we go. We have liftoff.
Propulsion continues to be nominal.
R68 chamber pressure looks good.
Following up. Roger, roger, planet.
Water towers fly! Yes!
Tango down to nominal.
Fighting downside SPD off. Bring in SPD off. Off. It's orange!
Orange 25! Oh my god! Oh my god!
Decollage.
What is it?
Put that in the big bag,
343 unfolds to go. Indeed.
We rise together, back to the moon and beyond.
This methane would be igniting in the flare, correct?
Yikes. You bet. We don't need any more of these.
All right. Well, as I said, this is going to be the 9th episode of Europe's Future in Space, where we talk about, the European spaceflight, but from the perspective of the officials that work on that spaceflight itself. This is going to be a rather interesting one because it's a unique sort of company, a propulsion company from both Spain and France. We have here the CEO of Pangea Aerospace, Adrià Argemí. Thank you for being here on NSF.
Thank you guys for inviting me, and it's a real pleasure to be here. I've been following your videos and being part of it. It's already a success.
And of course, thanks as well to DYs. They're going to be getting all of the questions from the chat. So you know the drill, tag at NASASpaceflight in chat. We're going to get your questions. We have usually our own set of questions, but maybe there's some others that we haven't thought about, and you may have those. So if you have those, tag at NASASpaceflight in chat. We'll bring those into the queue and be able to ask those questions to Adrià. And also at the same time, we have our producer, Jay Keegan, in the background, pulling the levers, pushing the buttons and everything. I think he only has one lever. But anyways, he also arranges these interviews. So thank you as well, Jay, for that sort of stuff. But, without further ado, let's get on to the meat of this interview because, European Aerospikes, we literally titled this interview, this episode like that. And that's one of the things that it's sort of, it's not normal to see Aerospikes in European spaceflight, right? Why did I'm going to start sort of from an unusual question, I guess, but this sort of episode sort of deserves that, which is why Aerospikes in the first place?
Okay, you started directly on the
Yeah.
topic. So, of course, our spikes are considered by many as just the holy grail of propulsion. So why Aerospike is because you could struggle a better performance. You could really struggle every centimeter or kilonewton of thrust out of the propellant. So the main reason is this. Then on how to do it, there's a lot of challenges behind, but I'm guessing that we'll discuss this. But mainly is the performance. And the performance now with the manufacturing thing, ways of doing, we can do it really in a cheap manner. So this is it. So until now it was I would say something that only NASA or the good old days at Apollo times could afford. Now we can have our spikes at a fraction of the cost. So the main reason is this performance, and now it's economically viable.
Yeah, I guess that's one of the things that with the evolution of spaceflight eventually gets down to a more achievable feat and goal to be able to do this. And so now, for real, like Pangea Aerospace was, I believe it was formed in 2018, right?
Correct.
How did it come about? Like, there's one time no Pangea Aerospace, now suddenly Pangea Aerospace. How did that happen?
Okay, so it started in this case. I myself, I'm an aerospace engineer, always propulsion expert, but I started my career on the aeronautical sector, working at Airbus. But I always wanted to go, noisier and taller and everything more sexier. And of course, rocket engines or rockets themselves are that way. And then decided to stop my work at Airbus and go to Italy to perform a master, and then um, start working at Avio, which is the second, I would say, largest rocket manufacturer in Europe with methane engines. And actually, into this master's, I already met part of my co-founding team that I briefly teased with the ideas on, hey, what about Aerospikes? How cool are they? I think it might be possible now. And is when we started. I convinced them, three other aerospace engineers. And then I convinced two other guys. Actually, yeah, you're showing this picture. The two, let's say, non-engineerings in order to make it, to fund it and to sell it. And this is how we started 7 years ago. It is true to explain the full story that we started with the Aerospike, yes, so this different type of propulsion system, but we wanted to do a full micro launcher. So we said, okay, let's be a reusable micro launcher with this, let's say, differentiation that having a better propulsion system. But then some years down, we said, okay, if it's better for us and doing a rocket itself, it's, as you know, guys, hard enough. Why don't actually sell the propulsion to others and becoming a specialist into this? And this is how we pivoted. And actually, it, of course, I'm biased, but it's playing quite well.
Yeah. And also, like, Pangea Aerospace, it sounds, I don't know, like, different, right? Like, it's a bit different than we usually hear.
The
What
name,
was
yeah.
the origin of that name? Yeah.
Of course, yeah, Pangea. So it comes from ancient Greek, pan and Gaia. So pan means all, and Gaia is earth. And since out of the six co-founders that we come from different, actually, countries from Europe. It was a way to put all together with one purpose. And also Pangea as well is what the supercontinent was named, back, I don't know how many millions of years ago, and the Earth. And since we make this analogy with a new space race, that we are just at the beginning. So we said, okay, it's, killing two birds with one stone. We love this Pangea, and we follow that trend of making many of our names be Pangea alike, I would say.
Yeah, and that's, I mean, we get a lot of companies, of course, this is the series Europe's Future in Space, but we usually get different companies from different countries, and they usually say, well, we are also like a European company, right? Like, even though it's just maybe one country, two countries coming together, or at least people from country or two, but then there's like people more joining from other places, and at the end of the day, that's what it counts, right?
Correct. I mean,
And
we were born as a European company, but space sector, I would say, is pretty global.
yeah.
It's one of the few peculiarities of this sector, the passion, and that it's the same and it's hard for everyone, no matter where you come from.
True. Really, really true. We've seen that recently as well.
Yeah, indeed.
And so, we're talking about, like, you were answering Aerospikes. It's efficient and whatnot, but maybe for people that don't understand, like, what is the advantages and maybe disadvantages, but you can probably talk about later down the line, like how you've solved some of the disadvantages as well of Aerospikes versus, a traditional engine bell nozzle kind of thing, right?
Yeah, sure. So what is an Aerospike? An Aerospike is just a type of rocket engine that it's different in shape when you compare it to a conventional one, bell shaped. And what it does is that it can really adapt to the ambient pressure. So it's many call them adaptive nozzle as well. So it doesn't care whether it's in the vacuum of space, in the moon, in Mars, or at sea level on Earth. So with one engine, you can go all the way up. Actually, the Aerospikes were firstly thought, as we were mentioning before, on the good old days of the Apollo mission, for Saturn V, they were really willing to transform the J2T, so the second and the third stage engine of Saturn V, to actually get more ISP and more performance out of it, and they decided to transform it into an Aerospike. Unfortunately, that never flew, but it's at the end what it gives you would be extracting the maximum performance of propellants into a nozzle. That would be the best way to put it. And also, it was intended to work on single stage orbits. So if you have an engine that works optimally throughout the full trajectory, why staging? Let's just have one vehicle that can do it, and this engine have the advantages to work always perfectly. So this is I would say the main difference. In terms of numbers, this performance increase could be, it varies, but more or less on the 15 to 20% more in terms of performance. So that could be translated directly into more kilos into orbit, or pounds, more payload into orbit. And of course, into a world of, you're making and you're spending millions of dollars and euros for 0.5% of something. If you have something to start with at 15, it gives you already a big margin to actually investigate it and go in and go deeper. So this, I would say, kind of the generic description of an Aerospike is this. Then it has a lot of challenges, and of course, it's they can be bigger in diameter, so you have to be careful with mass, because they can escalate pretty rapidly into mass. And I would say the more challenging one is thermal management, since you have a very big area to cool down. Actually, the throat of the Aerospike is the largest circumference diameter, whereas on a bell-shaped one, the throat is just the smallest circle. And normally in the throat is where you have the largest heat flux. And having a large heat flux and a large diameter, well, that's hard. You need a lot of mass flow rate actually to cool it down. And you have ways to solve it, and I can disclose more later on, but I would say as a initial description of Aerospikes and main advantages and disadvantages, I would say so.
Yeah, and so that is one of the things that it's usually being like that disadvantage of like, now I have to cool down this really big spike that we have to put here, the big throat, as you said as well. And so how do you manage that on your design? Because I've seen two different, we're going to talk about those as well, like two different designs. One that looks like it's just a small one, but then there's like another one with lots of little, more traditional bells, but then there's like the spike.
Correct.
What is the trade-off? Because I've seen also like multiple different types of Aerospike designs. There's also some others that are like virtual Aerospikes. So people might have already heard that from other companies out there, right? Like, how do you get around the different types of design of an Aerospike? Because it's quite complicated as well.
So I would say, to see a slightly more on let's say the description of an Aerospike, I should have mentioned that the Aerospikes could be linear. So it's just a line. Actually, I invite everyone that is listening us to check the Venture Star project, which was a Lockheed Martin-led single stage to orbit. So it was a linear Aerospike working with hydrogen. And also you have the ones that we are doing, the toroidal ones, like circumferential ones, because until now our clients are working on cylindrical rockets. The day they've been working on other type of shaped rockets, we might change that. So this to start with. Then, of course, you have inside the toroidal ones, you could have a single chamber, which is what we've done actually with our first demonstrator. that was called Demo P1. So it stands for, of course, Demonstrator Propulsion 1. Then we changed names. Fortunately, we were pretty bad at naming back then. The thing is to scale up that first engine that was more or less like this big. It was a 20, yeah, exactly this one, 20 kilonewton engine, so 2 tons of thrust. It was manageable, printable into one part. Actually, the engine was only 2 parts, so you're really reducing drastically and dramatically your part count. But then when you want to scale up that into a sellable engine that for several tons of thrust, it's very complicated on the manufacturing side. So that is why then we decided to apply our layout, which is having conventional bells sitting at a big plug. Of course, you're losing some performance there, but the overall still is a plus. So more or less, this is the justification why we've chose this layout. So at the end, we're working on our spikes, yes, but we are a propulsion company, so we have to master bells, our spikes, a little bit of everything, because not all our products are our spikes, but we have to master propulsion as a core, I would say.
Yeah, and that was sort of that was going to be my next question, of course, because now we talk about the Aerospikes, but now we're going to talk about the work that you guys have done, right? You mentioned the demo P1,
P1,
yeah, the P1, and then there's going to be a larger Aerospike as well, the one with the multiple traditional nozzle engines and things like that. And so, how do you go from the start of Pangea to getting to that first demonstration Aerospike, the P1 engine, right? Because I can imagine that it was probably through a lot of challenges, right?
Yeah, it's been a hell of a ride. I mean, it is still a hell of a ride. But that first, from foundation to the first test, it was bumpy for sure, to say the least. And actually, from the first, the classical FFF, family, friends, and full money, the first real money that get in to the roar of the P1 engine. So when we started from a PowerPoint to getting to test, it was 18 months. And we were pitching this to people. It's like, no, I mean, nobody has done an Aerospike before. And also as a first engine being an Aerospike fully 3D printed with a material that at that time was not available in Europe in only 2 parts. It was too many things that people were saying, come on, you're not going to make it. So we've learned the hard way. And so it was pretty ambitious project that turned out to be a huge success, and that we're still, and I hope I will take this to the grave as one of the epic moments of our lives. But it was complicated because one thing is you could have experience. We were a very small team, but doing it from scratch, something that you cannot go to literature and just copy the design. Or copy or inspire yourself. Of course, you can inspire, but then it's all of them are Bell. So it's like, for our spikes, we'll have to create our own, our own tools, our own software, our own models, apply margins wherever we could, and then the rest is history. And we went to DLR, to the German Space Agency, to test it, where actually the picture is on the video is, and it went well. Of course, we had to go. We had to convince a lot of people as well. There, like whenever they saw the piece the first day, like, no, this is not going to be mounted on the test stand, because have you leak tested? Have your pressure tested? And yes, look at all the test results. And the first test, I remember the first ignition test, we ignited on the first try, and the guys and ourselves were amazed, like, whoa, all the calculations worked. This thing, like, boom, it ignited. And last actually did not, when kaboom in some seconds.
Yeah, and we're seeing here, so I've got two things here to mention because we're seeing these pictures. First of all, the plume looks very bluish. What sort of fuel are
Mhm.
you using here for people that they don't
Methane.
know?
Yeah, indeed.
Cool.
I should have mentioned this. We're from very early days, we've decided to focus on methane. We do believe it's the propellant of the future, and actually, we're seeing a lot of companies now switching to it. So yeah, for us, it was a no-brainer. Let's focus on methane that you can actually biosource it. It's actually available on Mars. If some days there will be a nice Aerospike landing there. So yeah, it's methane. So it's very characteristic plume, this bluish color.
And also, you said that you went to the DLR, right? Like, is
Yeah,
that in Germany then? Those test
correct.
facilities?
Correct.
Okay.
It's in the German Space Agency because we do not have currently cryogenic test facilities. We do have our own test facilities for storable and in-space mobility that we can talk later. We are
Mhm.
now scaling up to have our own cryogenic facilities to not be dependent on going every time to Germany because it's cool, but it's expensive and not very flexible as a big institution. So we want to go as often as possible to test. And having your own test facilities, I think, is a no-brainer for a propulsion company. But making those are expensive.
Yeah. That's one of the neat things of, if there's already a player like the German space agency, right, that already has those facilities, you can just plug and play. Well,
Yeah,
plug and play, very in
absolutely.
quotes there, but it's a lot easier than having to build your own test stand from scratch. We're seeing some of those, like on that same video, it said something along the lines of like 5 minutes of burn
Yeah,
duration.
yeah.
How long did this test campaign last? Like you said, it was pretty much
So
18 months from foundation to first test, right?
yeah, the test campaign was something like 4 to 5 weeks, let's say a month,
Hmm.
month and a half. Of course, you cannot test every day. So you
Yeah.
test, I would say, twice a week. If you're lucky and you press and you get along with the guys there, you could convince them to do a third test day and everything goes well. So cumulatively, we run this P1 engine for this 5+ minutes. Actually, there's a lot of little anecdotes, but the last day that we tested it, we
Mm.
say, okay, fuck it, let's melt this thing and really see where the limits of it, and we failed. So we went, changing OF. We went to having uh, changing thrust as well. Let's push the limits of this, and it did perfectly. It withstood. Actually, the last day we ran out of propellants. We finished the propellants of the storage tanks, and we had to destroy it later on, the engine, to actually analyze it and see what was going on internally. But we did not have a kaboom in the test stand, which we were intentionally looking for.
That's great. We've already been live for like 20 minutes, and we already have so many questions. I'm seeing the chat here to my left, and it's scrolling by. So I'm gonna go to DYs because I'm sure there's gonna be lots of
Come on,
questions
yeah, go.
to throw at you. So take it, D.
All right. So first off, we've got a question here from 98 Central, wondering about the challenges of testing for different atmospheric pressures. So like you're testing on the ground, and obviously aerospikes are made to be good at different pressures, but how are you able to know that, with your
Yeah,
design?
good question. Actually, this is one of a major advantage of Aerospikes, that the same engine, you can test it on the sea level. If it's a vacuum engine, you have to have even a more expensive test facility to test on vacuum conditions. Of course, the first flight that we would do of our engines would be the real test of them in the upper stages, for example, upper stages version or the vacuum. And we rely on our models on heavily CFD to that. But one of the key advantages is the same engine. So if it performs as expected on the ground at sea level, we can very well derive how it will perform up there as well.
Nice. And of course, reusability is a huge topic in space
Yep.
flight now and only growing. So Gabriel is wondering if the Aerospike engine can be reused if you have reusability plans.
Yep. So not with P1, so our first demonstrator, but with ARCOS, which is our first commercial engine, which is a 75-ton, 750 kilonewton engine, made firstly for upper stage applications. We we are doing it and designing it for being reusable, but being reusable, I mean, it's hard. There are so many things that you have to take into account, and the good thing is that since from day one, we wanted to be reusable because we thought that reusability is a no-brainer. Everyone that is designing something that will not be reusable or not having plans on being reusable, we do believe that it's going to be economically doomed. It can be subsidized with national contract whatsoever, but it's going to be complicated. So in our case, we already introduced some variables to make sure that, for example, the chambers could withstand several cycles, as for example Merlin on Falcon 9 is doing. So our target is 10 missions to start with, and I can tell you it's already challenging because you have to do a lot of material characterization and a lot of analysis on, low cycle fatigue and how it would behave, because normally rocket engines were thought to work once, then you ditch them, you just build another one. And in the case of Aerospikes, to mention something more, there is a lot of reusability enabling capabilities as well. As you guys might know, Stoke Space, that is kind of it's not an Aerospike, it's more, I would say, a heat shield with some bells attached to it. But we do believe that Aerospike have this potentiality of adding Aerospike plug to act as a heat shield and then being a super performing engine, either for first stages or upper stages, because since it's the same engine, it had enabled reusability of any stage.
Nice. So we've got a couple more questions here about sort of the scalability. And so you mentioned a larger engine. But Adrian was wondering, like, if you're looking at, since you mentioned Falcon 9, a Falcon 9 sized vehicle for the first stage there, would that be several Aerospikes, one huge Aerospike? How does scalability really work?
Oh, that's a very good question. Okay, so several things to say here. So for the Aerospike is, how to mention it, is a performance generator rather than a thrust generator. So normally in the conventional two-stage orbit launch vehicles that we are used now, and I would say the majority of the companies are designing two stages. At the first stage, you want thrust. You just want to cluster bell engines, and actually it's way better because the thrust density, so the amount of kilonewtons per square meter, is larger if you can cluster several bells. Because the Aerospike, unfortunately, has the bells or the thrust generation only across its perimeter. So you're losing a lot of thrust density. So you could cluster Aerospikes, but then the diameter of the full rocket will become just gargantuous. So you could do it, yes, but I would say that for micro launchers, our engine could be a good first stage. If you want to go bigger, it's still very interesting to cluster bell engines and let the Aerospike shine on the upper stage.
Awesome. Well, we've got a lot more questions in the queue that we'll get to eventually. If anyone else in the chat has any questions, be sure to tag at NASASpaceflight. I'll try to organize those together. And with that, I think I will send it back over to Alex.
Yeah, I had in fact, prepared
Cool
a question
questions.
because I had literally one about the scalability of the rocket. Like,
Yeah.
say you had a 9-meter diameter rocket, right? That you had to put an Aerospike on. Yeah. That's one of the things that a lot of people ask about big rockets. Big rockets
Mm.
reusability is the number one question.
Yeah.
But yeah, you mentioned the bigger Aerospike, right? The Arcos Aerospike.
Arcus, yeah, correct.
So what is it about? Like what's the difference between that one and P1?
So, many, of course, for
Differences.
this, differences. The size, as I mentioned, P1 was 20 kilonewton. This one is 750 kilonewton engine. It's more or less 3.5 meters in diameter, so it's gigantic. So we're passing from not even 25 centimeters diameter to 3.5 meters. It's as I was saying, you can test it at sea level, even though it could be for upper stages or first stage application. It has a pretty big expansion ratio where it can go like 180, slightly even more. We're using a lot of our core technologies there. And we have a client already and client interest for that. And we're using it. Its first applications will be for an upper stage engine. And since it's Methalogs, we're targeting this 360 ISP, 360 seconds of ISP in vacuum.
360. Wow. Yeah.
Yeah.
That's so 3.5, you said 3.5 meters in diameter, right?
Yep.
So for people that may be watching, that's about the same size as the diameter of a Falcon 9 rocket, right? So like,
yeah,
talking, you said, how big was P1 again?
25 centimeters.
So
just your hand.
Yeah, from this to the size of a Falcon 9, pretty much, right? In terms of the diameter.
And one of the main differences, sorry, Alex, to cut you, as I was saying, the P1 is it was a single chamber full toroidal, and Arcus is several
each of these
chambers.
Right?
Yeah.
This is
Actually,
one of those
I have myself this little
no need for green screen.
mock-up here. Yeah. So, and this is it. So, of course, you want to augment the number of chambers you have. The more uniform the flow would be, the more alike the toroidal theoretical perfect one you would actually get to.
How many of these thrusters does it have? I'm calling them thrusters, but
call them thrusters. Right now we have 20. We're currently doing a lot of designs there, but with 20 we get everything that needed. And also interesting, this engine has no big heavy gimbal, so no moving parts. We have differential throttling, so we skipped having heavy gimbal, so it's directly attached to the second stage. And actually, since we have this interface ring that could be more or less adaptable to be as much plug and play as possible, because not every rocket has the same diameter. And this is something as well pretty interesting. So you can have directly the thrust loads go directly to the stage and not going through a gimbal to a thrust mount, and then from the thrust mount directly again to the stage. So there's a lot of innovation into these engines. There are a lot of challenges as well, and a lot of firsts.
Yeah, so you can essentially get rid of some of the intermediate structures and things like that.
Actually,
that's cool.
Compared to once again the classical way of doing two-stage to orbit. So I don't know. Let's put Falcon 9 engines on the bottom, one in the second stage. Normally, the more vacuum optimized you want to be, the longer your vacuum nozzle would be. So with our engines, you could get very compact and still retain all the performance, because with an Aerospikes, you could go with expansion ratios of, 400 even. And you can truncate it as much as you want. And even to a 20% truncation, you can still retain, 97, 98% of the plug performance, which is actually what's giving you this adaptation throughout all the trajectory.
Yeah, one of I remember one of the problems that they had when they upgraded Falcon 9, sort of the one of the latest upgrades was precisely getting that bell even longer to get more performance out of it. Now imagine if instead of the longer bell, just have the Aerospike instead, right? And then I can imagine
it would be
because
just
you can shorten the intrastage. Now you can make the tanks bigger and still be the same size, right? Sort of it compensates, I guess, in that sense. Yeah.
correct.
And you were mentioning, I'm pretty sure this is like hush hush top secret or something. You have interested parties already for that engine.
Yep.
It's
Correct.
completely secret for
It's
now.
completely secret. Yes.
Okay.
Unfortunately, I cannot tell you more, but yeah, we have customers already for this engine. As I said, for upper stage, this is only what I'm allowed to say. Otherwise, I'll be infringing some NDAs and some confidentiality, so they will come after me.
It's okay. We're not gonna get you in trouble
But yeah,
here or anything like
in
that.
due
But
time, we will communicate it.
we'll definitely keep an eye on that in our ears and all of our senses to be able to know which one it is. And you know, that's one of the things that I always sort of think about when you mentioned, for example, it's plug and play. Like how plug and play is it? Like you can put it on this interested customer, right? But if somebody else came around and they said, I want an Aerospike, but it's not Methalox, like could this design be modified for something that is not Methalox? Let's say
This has happened
Hydrolox?
already and happens many times whenever we talk to customers. And my answer is always the same. Yes, we could do it to hydrogen, but show me your pocket first, I would say, and their interest. And without being, of course, disrespectful, but our mission now is to demonstrate it with methane. Of course, if you put it with hydrogen, you still gain even more in performance because, as you guys know, hydrogen and liquid oxygen is the best propellant performance and combination, sorry. However, going to hydrogen, whoa, that's difficult as well. So it's already challenging enough. I would hope for the next live NASA spaceflight to be saying in some years, and now we're doing it the hydrogen way. Yeah, why not? So the modularity that we are actually offering comes more on the diameter, comes more on the thrust itself. We can have some slide variations, slightly up or slightly down. With still the same or slightly the same power pack. And this already gives a lot of freedom because, as you were saying, not every rocket is the same in sizes. And then if anyone are interested in changing propellants, we could have the discussion, but it's out of focus for us right now.
Yeah. And so we were talking about pretty much because one of the disadvantages or sort of like the challenges, if you will, of Aerospike engines is the cooling. And this is a bigger engine. And so you say that one of the changes precisely is that you go from the toroidal sort of thing to the different sort of thrusters, right? Around the spike. Is that like the only solution that you looked at, or maybe you were also thinking some other trade-offs as well there?
We thought to the first exercise we did is like, let's scale up demo P1 and see how it goes. And actually, also to comment on this, demo P1, so the first engine, it was already 20 kilonewtons, and it was the really smallest engine we could cool down. Because how we solve the thermal management in RFKs is that we're implementing a dual regenerative cooling system. We're using both propellants to cool it down. Because historically, rocket engines are just cooled with fuel. And normally you have way more oxidizers, so way more LOX. And LOX, of course, is not the best coolant in the world, but you have a lot. So let's use it. And since this was the firstly implemented in P1, we take this learning and escalate it to Arcus. So we're still using both propellants to cool several parts of the full engine, either the thrusters, the plug itself, because once again the plug is pretty large, and even though the thermal load on the plug is not as extreme as on the throats of the different thrusters, if you want, for example, this thing to withstand a re-entry, you have to take that into account. So on taking back to the question on reusability, you have to take the potential re-entry loads into consideration as well if you want to make them fully reusable.
Yeah, and that's one of the, so there's like another thing that I always think about when it comes to Aerospikes, because you said P1 was just 2 parts, which is a bit mind-blowing for an engine, right?
Yeah.
If I may say so. But for Arcos, that's definitely not going to be 2 parts, right? It's going to be
not 2
few
parts, way
more.
more than that. But still, since we are 3D printing, I would say 60 to 70% of the engine, we are doing a lot of, once again, this exercise of combining parts into single units. Of course, it's much more complex, and now designing the power pack as well. It's there, which is inside the engine. One of the advantages as well of the Aerospike, it's so big, but it's hollow inside. So you have a lot of space where you put stuff. And in our case, we put all the ECU, all the valves, the fit system, and of course the power pack, which I didn't mention, but it's a GG, it's a conventional
Gas generator,
gas
right?
generator cycle. Yeah, once again, to start with, we have plans to close the cycle later on Arcus, but one thing at a time. We have already several products ongoing in parallel. So yeah.
Yeah, part of that roadmap, so to speak, right? Of upgrading the engine and getting even better performance. I mean, with just gas generator and getting 360 seconds of ISP in vacuum, that's rather really
the
nice.
the beauty of our spikes. Yeah.
Yeah. And I probably have the question that no company wants to be asked, but I'm gonna ask it because I saw some of these videos and pictures were from 2023. I think some of the dates on the videos.
Yeah, we're currently testing. We have our test in Germany as we speak. So
yeah, what is the
hopefully
timeline to get one of the Arcos?
Okay. Yeah. So we're targeting our first flight before the end of this decade. This would be the political answer. I hope to be way before the end of this decade. So we have a first integrated test by the end of next year.
Nice.
This is our target. Because once again, testing an engine this big, it's another messy stuff to deal with, because it's not a 20 kilonewtons anymore. It's big, you have to move it around, etc., etc. But this is our timeline. Yeah. Integrated test, then integrated test with client, and hopefully first flight later on, and making an Aerospike flight. I mean, how cool is that?
Yeah. And I mean, every single time that I see this sort of testing is the thing in my mind of like, because there's gonna be, you said 20 of these thrusters, right? And so I was already looking at that, and I was like, I want to see the whole 20 of those thrusters. Is that going to be horizontal, vertical? Have you already planned ahead that sort of stuff as well?
The test time.
Yeah, the way that you're going to be testing that, or
it's going to be mainly vertical. For the first integration test already.
Okay. Yeah, because it's probably going to be a lot if you have to do that horizontal.
Because it's pretty big in diameter. So let's put it how it should go already from test.
Makes sense. Okay, I'm gonna go to D because I'm seeing already more questions here in our queue, and so I'm really curious what people might be asking.
Yeah, so we've got more questions coming up as we go. These two actually go pretty well together. We have Saad wondering about the throttle ability of Aerospike engines compared to more typical engines. Then we
Mhm.
also have Mike Smith wondering if maybe it could be used for reentry purposes.
Yep. Okay. So yes, I would start by the second one. Yes, it can be used for reentry purposes. We are inside a couple of projects with the French Space Agency analyzing all of this because, of course, we want to make them go up first, validate the performance, and that our clients are happy with that. But then later on, we want to demonstrate that their ability to act as a heat shield as well. And these the challenge is making work in Aerospike and then making it work as a heat shield. A little bit as we mentioned earlier, like the Stoke space idea. But yes, absolutely. We are already taking into account many re-entry loads and doing a lot of CFD, even let's call this a test on wind tunnels, supersonic wind tunnels, for seeing how it would react to that. And then the first one on throttleability. So in our case, with our layout, we are throttling up and down every single model. And this is how we have this differential throttling as well, and how we could direct and vector the thrust. And we are targeting more or less 50% to a slightly more 100 and 203 of the thrust in throttability.
Awesome. So this might be a really technical question, way more to get into, but I mean, lots of people have been interested in Aerospikes, but they've run into technical issues. And this one, Raj, is wondering, like, how have you worked to overcome some of the technical issues with Aerospike engines to make it practical for use?
Okay, so of course, is trying to simplify problems as much as possible wherever you can. Having first solved and learning from the thermal, because the thermal management, I would say, was the biggest thing to surpass. And then, as I said, while we're targeting and going with our spikes as our, I would say, the gem of our portfolio, but not the only one product we're working on, is to make them economically viable. So, of course, we know from history that Aerospike has been done if you have a big or large enough pockets. But the challenge here, and with the new space race, even though I don't like the new one, but this commercialization and this push for many players in the whole world for actually being commercially attractive, they want to be profitable. And if you want to be profitable, you cannot charge them, I don't know, like the RS-25 on the SLS, I don't know, 140 million per engine. That's not going to work. It's going to be complex. I mean, it's a different rocket, way bigger for different purposes, put man on the moon, etc. I know, but still, you have to really cut costs wherever. And I would say we encountered, and we will encounter more technical challenges, but I would say that the challenge now is the manufacturability, if that is even a word, of making every solution, every technical solution in a cheap enough way.
All right. Now, one more question we've got here is, can you talk about that logo on the side here? Can you explain what it means and its importance?
So the logo when we started the company, so you can see on the middle, it has this Aerospikey shape, and then the kind of the M it does is because it can go up and down from the curvature of the Earth, so it's reusable. So it had a purpose. This logo, yeah, that's the story behind it.
All right, that's really cool. With that, I will send it back to Alex again. Everyone in chat, keep your questions coming.
Yeah, nice question. Like that.
Yeah. So we've talked Aerospikes, but
Yeah.
what I've seen from the website and things like that of Pangea is that it's a propulsion company. So it's not just
Correct.
it's not just Aerospikes, right? You guys
Yeah.
are working on more things. Can you explain a little bit more
Sure.
what else
So
you're working on?
At the end, what I think is worth mentioning, Pangea Aerospace, of course, we started with the Aerospike, and we learned a lot on that, and we will learn a lot still and face many challenges for sure. But we want to become the go-to for propulsion. Every space mission needs propulsion. You need to get there. And the more people and the more companies are trying to get there, passing from the micro launcher to the next level, to the next medium launcher, even to the heavy or super heavy launcher, the more they are, the more they start thinking and making the trade-off, the make or buy. There is already solutions on propulsion. Why should I try to raise even more money and go doing it internally if I can buy a solution? So we want to become, I don't know, the Rolls-Royce of space, or the Arajet Rocketdyne, really proposing propulsion solutions for every step of the game. So you want to get access to space, I can give you big cryogenic engines, either for first stages, upper stages, Aerospike, not Aerospike. And then as well, once you are in space, with storable propellants, we have a full line dedicated on storability and storable propellants for in-space mobility, for you name it, OTVs, landers, key stages, satellites, platforms. So this is it. And of course, we're working with 3 different programs. So Arcus, as I said, on the Aerospike, Unix, the picture you're showing on the in-space mobility, and just from a year ago, we've been awarded a couple of contracts from European Space Agency and the French Space Agency to work on what we called or nicknamed Kronos, which is the biggest engine. That it's just the start of the journey, which is a full flow stage combustion Raptor-like, I would say, engine. But we're just at the beginning. But we're already de-risking a lot of the technologies that are needed to make a full flow Methalox engine a reality here in Europe.
Nice. And so we saw that Unix, is that the engine, the satellite, just for people to
No,
not
it's
get
just the
confused?
engine.
It's just the
Yeah,
engine.
no,
Okay.
we're working. We've, as I said at the beginning, we've started as a micro launcher company. We've pivoted. Now we are propulsion focused, full propulsion. You come to us because you need thrust. We are your guys.
Yeah, it's like on airplanes, right? You have the Boeings, Airbuses of the
Correct.
world, and now you've got the engine manufacturer, and they make the engines,
Exactly.
and they plug in on an A320 or 737 or something like that.
You got it. It's exactly this.
Yeah, and so this is an in-space engine, right? It's not. Well, I guess the Aerospike technically it's also in space, but you know what I mean, right? It's not on a rocket
absolutely.
creating big
Yeah,
thrust
our
and things like that.
in-space engines are conventional bell ones, because once again, the thermal issue for something that is super tiny, because our first engine was a 1 Newton engine for CubeSats, you cannot do it with Aerospikes. You have not enough mass flow rate to cool it down, as simple or as complex as it might sound.
Yeah, because you just said for CubeSats, right? So like that's really tiny, right?
CubeSats, yeah, super tiny, actually as big as your thumb. Yeah, this picture that you guys are showing is your thumb. Actually, in this case, burning HTP. So we are based our technology on HTP, so high test peroxide. So oxygenated water and Jet 1A, so kerosene as well. But it can work either on monopropellant or bipropellant fashion.
The irony that I made the comparison with airplane engines, and Jet A is sort of very similar to the fuel.
Jet A or RP1,
Yeah, and so
the purity.
And that's one of the interesting choices as well, because some other companies choose more traditional hydrazine. Others go with Hall effect thrusters as well instead of this sort of sort of
Mhm.
chemical rocket engines, right? So like, what was the trade-off there? Why did you choose the
Okay.
hydrogen peroxide / Jet A
So
design?
when we decided to go into the in-space market is
Mhm.
because we had some experience on the propulsion as a general topic. And of course, we're experts into liquid propulsion. Also is worth mentioning. We're not doing tomorrow solid or nuclear propulsion or electric one, as you mentioned, the Hall effect thrusters. So we're specialists into chemical one. And into this, when we did our trade-off in terms of propellants, many people has gone the N2O way. We've decided to go on the HTP. The main reasons is to first get rid of the toxicity of hydrogen. Hydrogen is great. Don't get me wrong. I mean, it's not that I don't like it. It works perfectly. There's a lot of knowledge of legacy, but the regulation point of view, if you want to simplify operations on ground and not having to have very costly operations, and the guys stood up in this almost scuba diving thing to just put iris in on the satellites, we thought it was interesting very to go that way. Of course, performance, HTP has a very good performance. It's scalable, and there is a lot of interest on as well on the European Space Agency, on the full European ecosystem, to move away from hydrogen, as I said. So all in this, we thought, okay, let's go for HCP. Once again, we've chose not the easy way, because once again, there was not a lot of knowledge, not a lot of articles talking about this, but little by little, you learn. And in this case, since we can test pretty rapidly because we have our own test facilities, you design, you manufacture, you test, you explode, and you test again. Yeah.
And you've been testing this engine for a while, right? Then.
Yep. Yeah. And hopefully, it will fly soon. So once again, for our first thruster, which is in this case we upscale it a little bit for 20 newtons, it's gonna fly if everything goes according to plan next year.
Okay. And what does, because you said it's called Unix, and it's like U-Nix.
Yeah.
What does that stand for? Because you also mentioned like P1. Oh my gosh,
Yeah.
we didn't name this. Also Arcos as
Yeah.
well. Can you explain those
Yeah,
names?
actually, we were thinking at some point we might change the names, but yeah, it's an internal discussion. This, so all Arcos, Chronos, Unix were kind of animals or dinosaurs or whatever kind of life they were present during the Pangea supercontinent time. So as you can see, we are pretty geeks as well, and we want to respect our name from early days. And in Nix, since we started for first a solution for CubeSats, and the CubeSats relies on the standards of the 1U, 2U, 3Us. Yeah. But again,
that's
we're
ingenious.
currently having this discussion. Okay, let's change it. We don't have yet a decision to, but that's the story behind it.
So with that wide range of different sort of propulsion solutions, if you will, right? The Aerospike engine, the in-space engine. You also mentioned Chronos, right, for the full flow stage combustion. Is that going to be like traditional Bell design, or?
Yep.
Okay.
Absolutely. For Unix, as I said, since the size, we're targeting conventional bells. Now for Chronos, we are targeting, because with our clients, which is institutions, they wanted the bell way, but we are doing our status to actually having closed cycles Aerospikes at this level of thrust as well, for potential upper stages, as we were commenting before on this thrust density thing, for heavy to super heavy launchers. But at the end is some core IP that we are generating that is, spread out the full portfolio of products. Of course, they differ a lot from super tiny things to gigantic thrust chambers, and they all have their own problems and challenges. But if you want to simplify it out, at the end, we are burning stuff, and we have to control it in a way that it doesn't it doesn't go into rapid and scheduled disassembly.
Yeah. And so with that wide range of different engine designs and propulsion systems and whatnot, did you see like a lot of demand from different, I guess for CubeSats and things like that, the Unix design, for example, that could be something that you sell a lot more because there's going to be a lot more
Yeah.
CubeSats in the future, right? Like, do you see
Yeah.
that sort of interest in the market?
We do. And the end, as we were saying, many people and many new companies are arising either on the satellite platform or the launchers that they want to go step bigger in designs. Many of them, they don't want to go fully internal again. So they said, oh, if this thing in whatever the time it would take you to finalize it and qualify it, you have it, and it's the good conditions, price condition, availability, how many could you produce, etc. People that were not even talking to us years ago now is like, actually, tell me a little bit more about it. And even this on the cryogenic big engines. And for the satellite market, it is true that it's a more crowded market. There's much more competition because there is no company specialized into cryogenic propulsion that wants to do exactly the same as we want to do us, whereas on the small part, yes. But we do believe that we have enough arguments on the performance-wise, on the scalability, and the knowledge to offer a very good quality product. Once again, performance to cost. This is our motto. It has to be good, but in the good ratio of prices, which is where we're seeing now the big trend of the space flight in general globally. Cost is the main driver.
Yeah, I remember when we interviewed, for example, Maya Space, one of their choices was precisely since they are a subsidiary of Aaron Group, they were like, well, they are already developing the Prometheus engine, so we'll take that and we'll concentrate on developing the tanks, the software, avionics, and et cetera, because the propulsion systems can take years and years to make, and this is something that they're already developing.
And because
so why we're going to be building this?
Indeed, at the end of the day, if once again you try to simplify hard problems, but a launch vehicle, a launch service provider is providing a service. The final client normally doesn't care if it's going in a blue rocket, yellow rocket, working on hydrogen, it's like, hey, tell me when I can go up and provide me a good service and a good accuracy actually of delivery. So this I think is a mindset shifting as well of our potential clients on the big rocket engines thing, that okay, I should focus on where I'm giving an added value to my client. And if there is, in the case of propulsion, a good solution in the market, let's take it and build upon this. And as we were commenting before, becoming more of a aeronautical mindset, where these launch service providers might become these large integrators that take this, the avionics from this, or working only on the tanks or the launch pads or the operations, and then having this very structured supply chain to actually go faster. And I think we should, on the space sector, learn a lot still from more mature industries like aeronautical or even automotive.
Yeah. And, especially with all of these different engine designs, I guess we sort of touched about this on this a little bit earlier, where you've got a bunch of customers asking for different products, and so you make you make an Aerospike, and you said that question of whether is it going to be hydrologs or something like that, and then you say, well, build a rocket, right? Like, is that something that drives also the long-term focus of Pangea? Like we've like you get a bunch of customers all at once, or very close in succession, and they're all like, oh, I want a Hydrolux. Like if something like that happens, would you say, okay, well, let's make like a parallel roadmap or something like that? Like, how can you adapt to the different sort of market shifts, if you will?
Yeah. So right now, what we are learning our way as we mature is being not scared of saying no, I would say. When you start a company, it's like, yeah, whatever potential customer you have, yeah, you want this? Yeah, sure, I can do it. But then as you grow, you start, okay, no, I need focus. So we would have the capability to steer the decisions in terms of propulsion of our potential clients and show them, okay, I have this. I think if I tweak it a little bit, it could be good for you. But we're saying, as I was answering before to your Hydrolux question, is I would not change now everything, all my roadmap, all my technology development, because
Yeah.
a client is asking me something different. Of course, it depends on the client, but still, we have a focus and we have to deliver and demonstrate to ourselves, to our clients, that we deliver, and later on, little by little, incrementing our portfolio of products with, I don't know, with more thrust ranges on the in-space mobility, with more cycles on the Aerospikes, closed, open, and then later on, why not changing on propellants? But right now,
Yeah.
it's because at the end of the day, as well, in terms of launchers, there are not 1,000 solutions if you want to go up there. So
Mm.
more or less, it depends on the size of the rocket, but they would go if they once again take into account as hypothesis the two-stage orbit, etc. We've done our homework, so we know more or less how to steer the conversation and show them that, okay, this could be good for this and this and this. If you are searching this thrust level, etc., I'm sorry, I cannot help you. I would love to, but it's not.
Yeah. I remember earlier in this review, you mentioned something along the lines of like having an Aerospike engine, being able to land on Mars as well, be part of a lander. And maybe one day that'll be the case,
Yeah.
right?
Let's see
Uh,
it cruise cruise out of Earth first, and
exactly.
then we can work on landers and whatever. But yeah, has a lot of
Yeah.
potential for sure.
Okay. Dee, do we have any more questions from the chat? Because I think we're approaching already our end here, so let's take some of those.
Yeah, we've got a couple more questions here. We have Raj wondering if you've explored the possibility of rotating detonation
Mhm.
rocket engines
I
and
was
sort of
expecting that
combining
one.
those with Aerospike engines.
Uh, we have not investigating it because the full combustion of an RD is another mess, I would say. Um, but we know that we've been approached in the past by some people doing that. It might be something to explore in the future, because for everyone here to know, yeah, the perfect combination of nozzle and an RDE would be an Arspike. So because the RDE since is already an annular gap forcing this detonation wave to go through, you can have a pretty big increase in performance in terms of ISP and also in thrust in a very contained space. And then our spikes plug nozzle later on, it's what gives you and makes it could make it shine. So yes, we've been approached. It could be cool. And this is Adri, the geek engineer speaking. Right now, we don't have let's say, a roadmap for that.
All right. We also have Jan wondering. So we've been really focused on the hardware and that propulsion. Obviously, there's some electronics and software required. So once this
Mhm.
technology is getting integrated into rockets, is some of that electronics work coming from you, or is that more customer side? Obviously, you don't have to go into detail there. I understand that might be
No, no.
uh,
What I can say, and we're developing in our case our engines to be plug and play, so they have everything inside. Of course, you have to talk first to your customer exactly what type of communication and telemetry you would require to control the engine, and they would require to actually control it. But we have actually on Arcus, we're working on having everything inside. So it has its own batteries, it has its own ECUs. You can plug it to your car, and if you have a big enough Methalog tanks, you can go for it because it could control itself. Then it depends of every customer. That some they say no, it's good, or some they say no, I'm providing you power and the controls on my onboard computer. I'm doing it up there, first stage or second stage. But right now we are doing it and designing it. Our baseline is that thing should be as much plug and play as possible.
Awesome. Now, the last one here is from Saad, who is wondering how big Pangea Aerospace is, if you can give a rough number of employees, and then I'll tack on to that. Are y'all hiring? I know we've got people from around the world who could be interested.
So yes, indeed. Thank you for that question and reminding me, DYs, as well on that. We are hiring. We are currently 70 people, and we are having 20 plus positions open. So hey, if you are interested and you have the right skill sets, just check them out. And yeah, we have actually a very multicultural team with 16 or 17 nationalities, and happy to expand that even more.
That is awesome. So I know we've got lots of people here. If you're interested, I was browsing through. There were engineering positions, there were technician positions, there were more management seeming positions, and there were also intern positions. So if you're qualified, be sure to check it out. And I will, at this point, send it back over to Alex.
Thank you, Wise, and for everyone for the questions.
Yeah. You know, that question about the jobs and things like that, it's always very important because, you know, maybe somebody might be watching and might be interested in working for your company. So that's always really important. And that leads me to sort of my usual last few questions, which is about European space, because obviously this show is Europe's future in space. It's a series about, you know, European companies, right? We bring here some of you guys and we ask questions about your companies, but it's all with the lens of this is Europe we're talking about. And it's not a place that when you talk about space has a lot of good press lately, right? And so how complicated would you say has probably been to go with your company than, I don't know, if you were, for example, in the United States, because it always sounds like, oh, the United States, it's got less paperwork and things like that, or Europe is always overregulated and things like that, or China, it's a lot, you know, different things. So how would you say is probably the comparison there?
So it's a pretty complex comparison and question, because at the end I have only one experience, which is creating a space company in Europe. So I don't know how easier it would have been in the US. Of course, whenever I go there, which I go quite often to conferences and visiting potential clients and suppliers, etc. You hear a lot of, oh, it's easier in the US, access to capital markets is easier. From my experience, it is true that at least the responsiveness of American capital is greater, in the sense the cliche, at least into my experience, is true. When you talk to American VCs, it's go, no go in like 2 or 3 weeks. In Europe, it could take months. At the end of the day, it's like, guys, your time is as valuable as mine. So you don't want to lose yours. I don't want to lose mine. So the access to capital, for sure, it's complex in Europe, not because there's no money, but as we're saying, space, it's not in the every everyday lives of people, even though it is, by cell phones, GPS connection, whatever, but they don't know. The majority of them, they don't know. I think there's a lot to improve into explaining and make them learn how important space technologies are. And since in Europe we are still 27 mindsets and not unified as we should, I'm a proud European and a believer that we should be more kind of the United States of Europe. In a way, of course, we could enter here into another kind of discussion for hours about politics and whatnot. But I would say that the access to capital is complex, and then there's a fragmentation as well of institutions. So you talk to the European Space Agency, but then you have to talk to your national space agency. Sometimes the priorities and the schedules and the agendas of both are not the same. And then you have the European Commission as well on the other side, that for some specific space-related programs, they are the decision makers. So you have to invest a lot of time traveling around, trying to convince many different institutions that at the end of the game, with a unified vision and leadership, might be easier. I'm potentially naive and utopian here, but at least we should, as European, push into that direction. So there's a lot of difficulties, but hey, Europe is now in this wake-up call moment for the geopolitical situation. So I think many acknowledgements are being done, like, oh, we have to get our shits done now and have this cohesion and cooperation way more than before, because otherwise we will be no one into the space ecosystem.
Yeah, and we saw, for example, this week the European Launcher Challenge being released by the European Space Agency, and I guess that sort of involvement might compensate what you mentioned about the private capital being a bit more complicated to get through. Like, probably,
of course,
that help from institutions, it's probably a positive, right?
Absolutely, it's positive. It's even though it's a not perfect program and there's a lot still into discussions, once again, politically, it's a good push for at least let the industry and the players propose what they have, and not being only politicians to design rockets, rather rocket scientists to design them and offer it to the market. So I think it's positive, of course, with its caveats, and I think it's demonstrating the good path. As I was saying, what we need is more institutional involvement to not to really feed the European spaceflight and really act as anchor customers for all these launch service providers, for potential new launchers to being developed, for new engines in our case, but new missions. So I think, yeah, it's a good movement on a good direction for sure. And there's a lot to learn from the US, actually. The US, the DoD acting as an anchor customer, or just NASA as well acting as an anchor customer. And it's happening here, but my thing here, my feeling and my thought, we need more cooperation as well, and the institutional world to really act with one single voice and becoming this anchor customer that all of us from European spaceflight ecosystem we need.
Yeah, because we see that in, as you mentioned, in the United States, you've got from NASA, from the Department of Defense, you've got different agencies even within the Department of Defense, the NRO, the US Space Force, and things like that. All of them giving multi-billion contracts to different launch companies or rocket engine companies as well. It doesn't need to be launchers, but also propulsion companies, Aerojet, Rocketdyne, Boeing, etc., etc. And so, like, that sort of support, it seems like it's sort of lacking here, right? For at least the greater majorities, it seems at least it's always the bigger players rather than more wider.
But it's changing. I can tell you that it's changing. It's, of course, there's a lot of friction, which in a way to see it is positive, because if there's friction, there's movement. But once again, there's a lot to improve, a lot to learn from other places in the world on how it's done there. And to me, it's again 27 unified wills and ambitions can go way farther that a single nation. I don't know, Spain, and we are based in Spain. It cannot go as far as we go as all together as Europeans.
Yeah, I really hope that obviously gets a lot better in the future, and we get a much more more powerful space sector, I guess,
Yeah.
in the future. But as
It is,
you know,
it's even on our scale, we're seeing that changed in the good direction.
yeah. And that's precisely sort of the whole deal with this series, right? Like, there's a lot of companies out there in Europe doing stuff and getting all of this together. And thank you for being here, Adrià, because this is one of those things that we wanted to incorporate in our series of shows, because it's like, rockets, satellites, and there's this propulsion company. Let's talk to them and bring them in and see what they have to say. And so, thank you for being here. I believe, Dee, we have no more questions. I already asked you in the back channel, but if there's any more, let's go ahead though.
I think we have just about covered everything here. Lots of thank yous in chat though for answering all these questions, coming on the show. This has been absolutely wonderful.
Yeah. Thank you guys for having me. It's been a pleasure, actually.
And thank you, Dee, as well for grabbing all of those questions, of course, and keeping an eye on chat and all that. And also thanks to Jay Keegan, the producer of the show. As I said before at the beginning, he also is managing all of these, getting into contact with different companies and whatnot. We have lots more companies in our list. There might be more Europe's Future in Space shows soon. We'll see about that. But until then, we'll see you all guys later. Have a good one.
And here we go.
We have liftoff.
Propulsion continues to be normal.
RCPA chamber pressure looks good.
Following up. Roger, roger, Atlantic.
Water towers fly! Yes! Tango down to nominal.
Flight downside of speed off. Bring in SPD off. Off.
It's orange!
Oh my god! Oh my god!
Décollage! Put that in the big bag,
343 unfolds to go.
Indeed.
We rise together back to the moon and beyond.
The methane will be igniting in the flare, correct?
Yikes. You good? Sure. We don't need any more of these.